Okay, there we go. Okay, hello everyone. This is the intro to gradient boosting machines. I'm Victor and I'm a workshop lead here at the University of Waterloo Data Science Club. And yeah, cool, double click. Yeah, so just to provide a brief overview, this workshop is targeted towards beginner to intermediate data scientists. I won't expect you to have too much knowledge coming into this, although some basic knowledge about decision trees, gradient descent algorithm, loss functions, just like general concepts with related to machine learning would be beneficial. And if you're confused on any of those concepts, we have plenty of workshop tutorials on YouTube that you can review at a later time. But the goals of this workshop we'll cover three main points. The first, we'll learn about Autoboost, which is like the precursor to gradient boosting machines. The two of them are pretty similar. So we'll start with Autoboost and then we'll compare and contrast and then move on to gradient boosting machines, where we'll start by looking at it for regression problems, since regression is more comprehensive. And then we'll look at how with a different loss function, we can customize a regression GBM into one that can be used for classification. So why should you attend this workshop or why you should listen the whole way through? Well, gradient boosting machines are super popular these days due to them being extremely flexible, since obviously they can do both classification and regression, but also just by you can use any differentiable loss function. And so you can use it for a variety of problems, and gradient boosting machines are a pretty popular choice. And it also, although it's a little bit more complex to tune, so tuning it properly is a little bit harder than for like random forests, which are kind of similar, but it does end up having a better performance when tuned right. And also, I lost what I was gonna say. But they're all, oh yeah, because gradient boosting machines use decision trees, they're also pretty interpretable, because you can see what the decisions are made at every single step. So not only is it flexible, it's also interpretable, which is a great point to have with machine learning models. So for a high level overview of how gradient boosting machines, or even just like boosting architectures work, we basically have a lot of weak learners that work together. So in terms of GBMs, we have a weak learner is like a small decision tree. And again, for those of you who are not too familiar with decision trees, they're basically like branching trees where you start at one node, and then depending on some features, like let's say if height is greater than 50, then you go to one of the branches, and then each of the leaves has a predicted value. So instead of having one humongous tree that helps basically classify your whole data set or a large portion of it, you have a lot of these smaller trees, and then all of them work together to solve your complex problem. And the models are sequential, so the models are created sequentially, meaning the ones that are created afterwards, like the second one would reduce the error of the previous one. And so by this way, as you learn more and more, add more and more of these weak learners, they improve on the classification of the previous ones, and then as a group, they are able to solve very complex problems. So let's jump right into Autoboost. So here is just an overview of the steps, and we'll get into each of these the details of each of these steps further. But for now, so we start off by giving each training example a weight, and this weight will basically tell us how much we want to emphasize classifying this example properly in like the next tree that's going to be created. And the second step is adding a decision stump based on minimum weighted error. So here I say decision stump instead of decision tree because Autoboost only uses stumps. And what a stump is basically, you can see here, it has one node which has two leaves, right? So it's literally like if height is greater than 50, yes, otherwise no. It doesn't get more complex than that. Autoboost only uses decision stumps. And we also, so we created decision, we added decision stump to our model based on the minimum weighted error, where the weight is the weight that we gave the training examples previously. We'll see this in more detail later. So then once we added a stump, we compute the final error of the model plus this new stump. And then we also compute the influence. So the influence, aka the amount of say that this decision stump has is basically how much emphasis this decision stump's classification will end up being in the final model. So like in this example here, you see that like this one is much bigger than like this one here. So the result of this decision stump will be more heavily weighted than the decision of like this stump when we are actually predicting, right? So that's in terms of like the whole model. And then we also, after we've computed these, we then reweigh each of the training examples. So any of the examples that were predicted incorrectly will give more weight so that the next decision stump that we create will be more likely to predict those ones correctly. And so that's how we repeat and make sure that each of the examples are hopefully classified somewhere down the line. So let's see this in more detail. So here we have this data set where we're trying to predict the heart disease given a patient's chest pain, whether they have chest pain, blocked arteries, and their weight, right? So we'll first initialize their weights. And again, so we'll start by putting them all to equal weights. And since there's 8 examples here, we'll just give all of them a sample weight of 1/8. And also all the weights have to add up to 1. And so now we'll create a decision stump based off of the data set and the weights. And I won't get into too much any detail about how to actually create the stump or how to create any decision trees, because there are a lot of different methods and I could probably spend a whole hour on different ways to create optimal decision tree based on data. So we'll just assume that somebody has told us what the most optimal decision stump is at every single step. So in this case, let's say we have this decision tree, decision stump, where we just say if the weight is greater than 172, then we produce yes, otherwise we produce no, right? And so based off of these patient weights, we get the new classifications, right? And we can see that this is pretty similar to the expected heart disease output, right? Except for this row here, right? This one was predicted incorrectly. So now that we have this classification, we can now compute the errors and influence. So here's the formula for total error. It is the number of incorrectly classified examples divided by the number of total examples. And in this case, since we have only one incorrectly classified example here, it's 1 divided by 8. And then that's a total error. Now for the influence, it's this somewhat ugly number, somewhat ugly formula, and then this comes out to 0.973, but we can plot a graph of influence versus total error. So here we have total error on the x-axis and influence on the y-axis. So you can see that as total error decreases, aka goes closer to 0, then the influence is much higher. Whereas when the total error is much larger, then it influence is smaller and even negative, right? So if influence is negative, that means that we actually classify more of them wrong than we actually classify right. But anyway, so yeah, so the higher the number, the bigger the influence, and therefore the bigger amount of say that this decision stump that we just added will have in our final model, right? So that's that. And then now we'll compute the new weights based off of this tree's influence. So we have two cases, one where it was classified correctly by this model and one where it's classified incorrectly. And so we basically, the formula is the new weight is equal to the previous weight times e to the negative influence for correct and e to the influence for incorrect, right? So, oh, this is, I wrote this wrong, but the final answer is correct. But so in this case, it should be 1/8 times e to the negative 0.973, which is the influence here, and we get 0.047. And so you'll notice, again, this is incorrect. It should be 1/8, but that is 0.125. And the new weight is 0.047. And so that is much smaller than the previous weight. For the incorrect one, we have 1/8 times e to the 0.973, and we get 0.33, right? And so this is much larger than our previous weight. And so this way, when it comes to the next iteration, we'll have much more weight in the incorrect samples. And so we can focus on classifying those ones correctly for the next decision stump. And so we can see the new column here, right? So all the correct ones, which is basically all of them except for this row here, is 0.047. And this row is 0.33 because it was classified incorrectly, right? And obviously, these weights do not add up to 1. So we basically scale all of them up by a constant factor. And then, so now all these, other than rounding, will add up to 1. So now we take these new weights and we repeat. So here's the data set on the left here again. And then here we have the new sample weights. So 0.07, except for this one row, which is 0.49. And then we, again, create a new decision tree. Again, I won't go into details on how this is created, but assuming this is the most optimal decision stump that we can add, we reclassify the data set. And then now this one obviously is classified correctly now, but now we have these two that are classified incorrectly, right? But obviously this one was much higher weight, so we made sure to classify this one correctly. And then again, we can classify or compute the errors. So in this case, we have 2 of them that are incorrect. So it's 2 out of 8. The influence is much lower this time because we have more of them that are classified incorrectly. So this decision stump will have a little bit less influence in the amount of say in the final model, but also have some say, of course. And then we recompute the correct and incorrect, right? So we have correct multiplied the 2 by the 2 different previous weights. 0.07 is reduced to 0.04 and 0.49 is reduced to 0.28. And then we have the 2 incorrect examples with weight 0.07, and then those are increased to 0.121, right? So then that gets thrown into this column here. And again, we rescale everything up to add up to 1 again here. So yeah, notice that it's still, this sample is still classified pretty highly. Again, because of the fact that the influence of the tree that we just added is quite a bit smaller than the first tree that we added. So we still need to make sure we classify this one correctly. But also, again, we want to make sure that we also classify these ones correctly as well. But yeah, so we basically keep on repeating until we're satisfied with the classification. And we just get the result will be a bunch of these decision stumps, and each of them will be scaled by their influence, right? So like the first one has a scale factor of 0.973, the second one has a scale factor of 0.549, and dot, dot, dot. It's not necessarily decreasing, it's just how this example happened to be. But we'll just have a bunch of these training stumps, and this will be our model. When we do prediction, we'll just run it through each of the decision trees and then take the weighted average of each of the results. And that's Autoboost. Again, well, I didn't really go into any of the math because this math is I want to focus on gradient boosting machines, so we'll go into the math with GBMs. But if you're interested in looking at the math for Autoboost, there's online sources. But I wanted to keep that simple as a kind of like an introduction to GBMs. But I'll take a pause here. If anybody has any questions, let me know. Cool, so I'll take that as a no. So now let's get into GBMs. Or at least the difference between Autoboost and GBM. So we previously saw that Autoboost uses decision stumps, where GBMs instead uses small decision trees. And these decision trees are usually have 8 to 32 leaves, but still much smaller than your data set, which probably has like thousands, millions, or even billions of like examples. So they're still relatively small in comparison to like random forests. I think they use much larger decision trees than gradient boosting machines or somewhere similar. But at least GBMs, the trees are slightly larger than the stumps. Better for prediction. And then also we have Autoboost. Each of the trees predict the actual classification. So we saw it either predict yes and no. Whereas we'll see in GBMs, they predict residuals. So instead of like the actual result, we have the result here as the initial prediction, and then we just predict the difference or how we want to change the prediction to match the actual expected. So let's say we have like 50 here, and then we'll have, we'll have 50 here, and then we'll, let's say, add 5 here, and then minus 7 here. So we're not predicting the actual output for each tree does not predict the actual output. It just predicts the difference between the previous prediction and the expected output. And then one final difference is that in Autoboost, each of the trees are scaled individually. So like this one here is scaled much higher than larger than this one. Whereas in GBM, all of them are scaled in the exact same way. And we'll see how this relates to gradient descent. But anyway, so let's jump right into gradient boosting machines. So again, here we'll go into just a brief overview of the steps in gradient boosting, and then we'll jump into the details for each of the steps. So we'll start by initializing prediction. So that will be our initial prediction. And then we'll compute the pseudo residuals. I'll get into why it's called pseudo residuals later. But you can kind of think of this as like the difference between the expected prediction and our like initialized or like previous prediction. And then from these residuals, we will create a decision tree to predict those residuals based off of the features in our input. We'll then add that decision tree that we just created to the ensemble of models with a certain learning rate. This would be like 0.1 or something relatively small. And then we'll recompute the new prediction with the new decision tree in our ensemble, and then we'll just repeat, right? Then get the new residuals, create a new decision tree, yada, yada, yada. Right? So let's get into the details. Here, we'll use a slightly different data set. We'll start with regression, again, because it's more general, and we'll see how it, like classification is like a specific case of regression later on. The math is a little bit nicer for regression too. So here we have this data set, right? So we're trying to predict the price of different cars, where we're given like the row. Well, okay, the row number doesn't really apply, but cylinder number, and then the car height and the engine location, right? So here are the prices that we want to predict, and then we initialize our initial prediction, right? And you can think intuitively it makes sense to just take the average of the 4 prices, and that'll be our initial prediction. But we want this to also make mathematical sense, right? So here's the actual math to why we take the average to get the optimal prediction. So to interpret this, this is f sub 0 of x. X here is the input. So like going back, this will be like the cylinder number, car height, engine location, and f is the prediction, right? And the 0 is the iteration number, right? So this is the initial prediction, so this is 0, right? So basically the optimal prediction for off of our input at step 0 is this optimization where we minimize, we find the gamma that minimizes the loss between yi, which is the expected price, expected value, which is the price in this case, and gamma, which is supposedly the prediction, right? And we want to minimize the sum of some loss between these two, right? And the most common loss you can think of, probably, at least for regression, is mean squared error, right? You want to minimize the square distance between like the price and our prediction, right? So we'll take something similar, except for, so you'll see like mean squared error is like this part here, but we add a 1/2 here, right? And I'll get into exactly why we use the half later on, but notice that since this is a minimum optimization, adding a half doesn't really change the output, right? The gamma is still going to be the same, even if this whole value gets scaled up by a certain amount or scaled down. So anyway, so our loss in this case is just a scaled version of a mean squared error, right? And so how do we find the optimal gamma that minimizes? Well, we take the derivative, right? So in this case, the 2 cancels out with the half, and then we pull out the negative. Again, this is just simple calculus, but this is a derivative, and then we set that equal to 0, do some rearranging. Notice that gamma doesn't depend on I. Again, in this case, because we have the same prediction for all of them. So we move that out and rearrange, and we get this value, which is basically the average of all the expected prices. So that is why, given this loss function, the minimum, the prediction that gives us the minimum loss is the average of the prices. So that's the intuition behind why we take the average. But anyways, so now, okay, I'm not sure why this came up so fast, but anyway, so now we compute the pseudo residuals, right? So the residual in this case is the price minus the prediction, right? AKA the difference between the two. And the reason why this is called pseudo residuals is because this is not the residuals that you would see in a regular regression. In that this like price minus prediction comes out because of the fact that we're using this certain loss function. If we use a different loss function, it would look completely different. But in this case, we have that the residual is equal to the negative of the gradient, where the gradient, if you remember from before, looks something like this. And we just use a negative sign. And so you'll notice, if you're familiar with gradient descent, you'll notice that this is really similar. In fact, this is, well, we're literally doing the gradient descent algorithm, right? Because remember that the gradient of a function is basically, when we're doing gradient descent, we want to go in the inverse direction of the gradient to move our prediction towards the expected value, right? So we're finding basically the gradient of the loss with respect to our prediction. And then we want to move in the negative direction. So that is what we're literally doing. We're literally finding the gradient of the prediction and the price, right? So in this case, the price is 12,000. Our prediction is 14,500. So we want to move in the negative 2,500 direction, right? And then, so this might also make sense as to why we have learning rates later on. But yeah, so basically our residuals, you can kind of just think of it as the gradients. And this is a direction that we want to move our prediction in to make our prediction closer to the price, right? So, and again, this residual is price minus our previous prediction only because of the fact that we are using this loss function. If we used it something different, the gradient would look something different and the residual would not actually be a residual. It would just be called a residual, but it would be computed in a different way. So that's why it's pseudo residual. But anyway, so now that we have our residuals, now we create a decision tree to predict these residuals. So in this case, I have this 2-layer 4-leaf decision tree. And again, I won't go into details of how to create this decision tree, but here, and again, technically, if the decision tree had 4 leaves, and my data set only has 4 rows, I could perfectly classify each of the examples, but I don't want to do that because most of the time you won't have a perfect classification. So I just wanted to move one of the leaves, join 2 of the leaves just for generality's sake. So in this case here, we have 2 layers. We start by splitting on height between less than 52.4 and greater than, and then cylinder number. And then so now we have 3 residual groups, right? Again, I'm kind of combining the 2 middle ones here. But we have the negative 2,500 fall into this one, the 2,100 fall into the middle, and then the negative 500 fall into the third one here, right? And so now we got to figure out how do we actually combine these two. And again, it might make intuitive sense that we want to just take the average of the residuals. But again, there's mathematical proof behind why we actually take the average. So here you'll notice where it's pretty similar to what we had before, where finding the gamma that minimizes the loss between the expected value and the previous. Here M represents the iteration number and J represents the which residual group. So like for this one here, we'll use J is equal to 2. And since this is our first iteration, M will be equal to 1. And remember that F0 is your the 14,500 for all the different examples. We're minimizing the loss between the expected value and our previous prediction plus this new gamma that will be the result of this residual group, right? Again, we're using the half mean squared error loss, and then we find the derivative, solve, and then we find that it is equal to basically the average of the residuals that are in the group, right? And again, this is highly dependent on the loss function that you choose. If you chose a different loss function, the resulting value that would come from this residual group would be different. And we'll see that in classification because it's slightly different there, but we'll get into the details of that later. So basically we have a decision tree where the first one produces negative 2,500. The second one will be the average of these two. So it'll be 1,500. And then the result of this one would be negative 500. So then we update our prediction, right? So new prediction is equal to the previous prediction plus the learning rate times the tree made on residuals. And again, remember that the tree basically predicts the residuals, aka the gradients. So we're literally taking the previous prediction and then moving it in the direction of the gradient multiplied by some learning rate. And that's why this whole model is called gradient boosting. because we're literally boosting our gradient with every single decision tree. So yeah, in this case, we have the new prediction is equal to 14,500 plus 0.1, which is our learning rate in this case, times this tree that we just created, right? And then you can see the result here. So we have our expected price. We have our old prediction, which is just the 14,500 for all of them. And then we have the new prediction. And so notice whenever the price is lower than the old prediction, our new prediction is also lower than the old prediction, right? Because we're moving the old prediction in the direction of the price. But notice this is just a small step. And so that's why we need to repeat. So yeah, we take the price, we take the new prediction, we find a new residual, right? It's different. And then we create a new decision tree. We repeat the whole process. And so now our new prediction has 3 steps: initial plus the first tree plus the second tree, right? And this could go on for as many trees as you want. So yeah, most of the time the parameters that you'll have is like how big you want each of the individual trees, how many trees you want in the resulting model, and like the learning rate. Otherwise, everything else kind of just happens automatically. But yeah, so just to recap, we create initial prediction for regression and the loss function that I was using the whole time. We take the average of the target values. Then we compute the pseudo residuals for every single training example, which will be like the gradients. And then we create a decision tree for predicting those residuals. Then we'll add that decision tree to the ensemble of models with learning with a certain learning rate, and then we'll recompute the prediction and then repeat. So that's gradient boosting. I'll go back here and take another pause for any questions. But yeah, it's not too complicated. Everything kind of just depends on the loss function that you choose at the very start, and everything else just kind of follows through in the creation of, well, the creation of the decision tree is kind of separate, but how the trees are combined together is
Can you hear
kind
me?
of happens automatically. Yep, I can hear
Good.
you.
All right. So I want to ask, like, sometime when we are having a lot of tree, like the tree can go deep, right? And it can speed up the training process. And if we don't have GPU, I know like some algorithms support GPU, we can just use, but if we don't have GPU, is there any way we can speed up the training, like any parameter that we can change to speed up the training?
Yeah, so that has XGBoost, which is like the leading version of gradient boosting machines, does have a number of optimizations onto this process. I won't cover XGBoost in this workshop because I could probably spend a whole 1 hour on the different ways that XGBoost improves on this algorithm. But you can like, the bulk of the time spent for this is coming up with the decision trees. So you can optimize it by like reducing the number of different ways you can check for the optimal decision tree, and as well as like parallelizing the computation of these residuals. Like for XGBoost, I think it just creates a histogram of the residuals, like an approximate histogram rather than like all the individual residuals. And so there are ways to speed it up in terms of like the creation of the decision trees, because that's what takes the most of the time. But otherwise, the rest of the model kind of happens pretty quickly. I don't know if that answered your question.
Yeah, sure. Thank you.
Cool. Yeah. Maybe in a later workshop, we'll cover XGBoost, and then you can learn more about some of the optimizations related to that. But that was a pretty good question. Anyways, any other questions? Yeah, again, if not, if you do have any, feel free to put in the chat or just feel free to interrupt me. Always open for questions. But yeah, so now let's talk about classification. So classification is literally basically uses the exact same concept. It's just that we're using a different loss function and the interpretation of our predictions are a little bit different. So in this case here, we have this like sample data set here where we have the input is like popcorn age and favorite color, and then we're trying to predict whether or not they love this movie Trolls 2, and it's like a yes or no question. So here, we could try to predict. I mean, like the most intuitive way you can think of just going from regression to classification is you predict a value between 0 and 1, aka the probability of whether or not it is like yes or no. And then if it's greater than 0.5, then you just classify it as yes. If it's less than 0.5, then you classify it as no. So that is one way you could extend regression to classification. But one problem with that is the fact that it's bounded between 0 and 1, but a decision tree itself is not bounded in any way, right? And so it could give you a prediction of 2, and you take that 2 and go like, what does this even mean, right? So we can map probabilities to the real number line, aka from negative infinity to positive infinity, by using what's called the log odds. And log odds is basically the log of the odds, and where odds represents the number of one class divided by the number of the second class. So the number of yeses divided by the number of nos, right? So you can see here, I'm computing the log odds of this column here. So we have 4 yeses and 2 nos. So the log odds is log of 4 divided by 2, which is equal to 0.7, right? And oh yeah, I was supposed to add a slide on how to actually compute this, but I'll show the actual formula for computing log odds from probability and vice versa when we get to the notebook section. But it's just log and exponentiation, and then you can use the inverse of that function to recover the probability. And these two are the same just due to rounding right now, but they're actually very different if you give it more digits. Like this one should be 0.69, this one's like 0.67 or something. But anyways, so yeah, but in this case, where instead of predicting the probability, we try to predict the log odds, and then at the very, very end, we convert that log odds into a probability and use that for classification, right? So just to summarize, we predict log odds because it is along the real number line. It has values from negative infinity to positive infinity, which is the exact same as for a regression problem. And then we transform that to a probability at the very end of prediction. So in this case, yeah, so then we can find a residual, right? We get the probability from the log odds, which is 0.7, and then we take the residual between yes would be like 1 and no is 0, right? And then that's the residual, right? And in this case, we can't really use mean squared error anymore because we have a classification problem. So instead we use cross entropy. And so this is probably pretty familiar to those of you who have done that. It's the if yi is yes, then we take the log of the expected probability. Otherwise, if it's no, then we take the log of 1 minus the probability. And you'll notice that we have an extra minus sign here, and similar to the 1/2 that we had previously when we were doing regression, this is literally just to make our life simple when it comes to computing residuals. Because you'll notice that once you, this is in terms of probability, and this is in terms of the gammas, aka the log odds that we're trying to predict. But if you find a derivative and go through the calculus, you'll notice that the residuals is the exact same as the one that we had previously for regression, where we have the expected yi minus the probability that we're predicting. And this is just like the transformed version of our gamma, which is the log odds that we're predicting. Okay, so you can think of P and gamma to be basically the same, it just transformed. One is between 0 and 1, and one is between -infinity to infinity, and one-to-one mapping. But anyway, so that's how we get these residuals, right? So it's the expected minus the given probability. In this case, it's 0.7. So it's 1 minus 0.7 and 0 minus 0.7. And then we get into the messy part. So that computing residuals is fine. We then create the decision tree. We throw the residuals into each of them. But remember, the residuals is a difference in probabilities, right? It's 1 minus the probability computed from the log odds. Well, we need to transform this to a log odds. And so that happens when we do this optimization here, right? Because we want to find the minimum gamma, aka the log odds, such that we minimize the loss between the expected value and the previous prediction plus the new gamma for all of the training examples in this residual group, right? So in this one, we're minimizing these two. And the math behind this one is super messy. So I'm gonna spare you all the details because it goes into a lot of advanced calculus, including like Taylor approximation. So, and like, I saw a video on this and like took 30 minutes just to explain the math behind this. So I won't go into that, but the result gets to basically the predicted log odds that we want to add to our model for this residual group is the sum of the residuals divided by, and this one is this, remember, xi is the input, f is the prediction, previous prediction, and then p is just the transformation. Remember, because the previous prediction is in log odds, we transform that to a probability. So, and that's just kind of simplified in this this one here. So the sum of the residuals divided by the sum of the previous probability times 1 minus the probability for each training example for the previous model, right? So it's not exactly the most simple formula, but it's purely just calculus derivation such that we can minimize the loss function. And again, this will look completely different if we use the completely different loss function. This is just the result if we use cross entropy. And we'll kind of see it in action later on. But yeah, so that's basically the only two changes that you need to make for classification. You just use a new loss function and interpret everything as log odds, and all of the details kind of just happen automatically. The computation of the residuals, the computation of the log odds, predicted values from each decision tree are all kind of just happen automatically just by choosing a different loss function. Of course, that's assuming that the loss function is differentiable. So you cannot use gradient boosting machines with a non-differentiable loss function. But otherwise, it's super flexible. I mean, we just transformed the regression problem into a classification problem just by changing the loss function. So, and obviously this is for simple problems. If you have a really complex function, as long as you have a differentiable loss function, you can basically solve any problem with gradient boosting machines. And so that's it for the presentation part of this. Let me go into the notebook session. Okay, I lost the highlight. Can you all see the notebook? Cool, awesome. Okay, just making sure because I don't see the border that shows me what I'm sharing. But anyway, so let's get into actually using it gradient boosting. So here we'll import just the standard stuff, matplotlib, numpy and pandas. And then scikit-learn provides us this gradient boosting classifier already implemented, so we don't have to actually implement it ourselves. And then we'll load some data. Yeah, so I need to connect, add training data here. And I'm just using the Titanic data set. So here we'll just take a look at what train looks like. But it's just passenger ID, whether or not they survived, passenger class, name, sex, age, all these columns, and we're trying to predict whether or not they survived based off of the other attributes. So a classic Titanic example. So we'll just clean up the data a little bit. We'll set the passenger ID as the index, and we'll split off the survived into its own section, because gradient boosting machines will literally take every single column and try to fit a feature to it. So we need to be careful of what features exist in training set, because it will try to use those. So we split off survived into its own variable, and then we also drop some of the things that aren't exactly useful in terms of actually predicting, like name, whether or not they have siblings, that kind of stuff. So we'll drop those columns, and then we'll convert sex to like an indicator variable rather than like female and male, just to make it a little bit easier for the model to interpret. So now and then we also fill all the NA values, which is 0. So now we have our training set, which has P class, age, fair, sex male, sex female, sex male, and this has a shape of, oh, I didn't run this, of 891 and 5. So we have 891 training examples and 5 features. And so we'll just fit our classifier. So let's start with learning rate. I'm putting this as 1 because we'll see later, but if it's too small, we won't actually see the impact of each of the decision trees, and we'll kind of look at how the decision tree works later on. So I'm just putting this learning rate as a bit higher than you would normally. But anyways, we created decision boosting classifier class. We get the estimators, number of features, learning rate, max features. These are just kind of standard parameters. Like max depth is how many layers each of the individual decision trees will have. So these are hyperparameters that you would need to tune, and then we fit our classifier onto our training data, X and Y. We can find the accuracy score is 0.817. And number of estimators is number of decision trees that we're using. So with just 5 decision trees, each of which has only 4 leaves, we get an accuracy score of like 8.817. And if we, yeah, so now we can kind of visualize. Scikit-learn also has some nice visualization for decision trees. So we can look at the first decision tree here. So the first one just checks if they are not male, aka sex male is less than 0.5, then we check the fair, and then we have each of these 4 values. And it also says how many samples, aka training examples, fit into each of these, right? And so remember, this is classification, so each of these values are log odds. So the higher the number, the higher the resulting probability. And yes, and then so this is the first decision tree. We can then look at the second decision tree, and it would look like something different. This one goes on fair, P class, and age. But anyways, let's just go back to the very first one. And we'll kind of like go through it step by step. So let's actually put this back to 1. Let's just assume we only have 1 estimator. 1 decision tree still has an accuracy score of like 0.788. And so this is literally our model only has this one decision tree in it. And so we'll kind of just see it step by step. So I also have these two functions, helper functions here. And this is to transform the probability into log odds. So you take the probability divided by 1 minus the probability, and then you log that. Because you remember odds is the number in one class divided the probability of one class divided by the probability of the other class, and then log of the odds, right? So that's kind of simple. And then you just invert that to get the conversion between log odds to probability. So that's just the helper function for that. And then let's just say we have this extra piece of data that we want to predict, right? I kind of just put in random values here. And so let's say, so now we remember we have two steps. One is initialization, and then we add on the learning rate times the result of the decision tree, right? So we can get the initial estimator by doing GB, did I do GBM or GB dot init, and this produces an estimate. Oh, I need to run these, just making sure. This is dummy classifier, and the default dummy classifier basically says you just take the most, you basically just take the probability of like the average probability, right? So we can look at that by doing X train. We can take the sum of Y train. Remember, Y train is literally just the ones and zeros that represent whether or not they survived. So we can do the sum of that divided by the length of that to get the average, right? So this is like the probability, average probability of someone surviving, 0.38. So the dummy classifier would say like 61% of the time they'll fail. So let's just throw all of them to fail. But anyway, so that's that. And then we want to add the result of the decision tree, right? So we'll take, I set this value here. So subtree 0 is the 0th estimator. So we'll take subtree 0, and then we'll predict on X dot toNumPy. And then, so this is 2.6. You can see that right here. And that makes sense because we have, right, so like if we can follow the decision tree, sex male is 1. So if this is false, we go down here, age is less than or equal to 77. We have 100 here, so it's false again. So we fall under this branch of the decision tree, this leaf. So that's why the value is 2.6. And then we then add, let's just set this to initial prediction is equal to this. And then we'll say this is like predicted log odds or something is equal to that. And then we add them all together. Oh yeah, but initial prediction, remember this is a probability, so we need to actually transform this to log odds. So initial log odds is equal to probability to log odds of our initial prediction. This should actually be like initial probability. And then we'll just add these together. So this plus the learning rate times our predicted log odds. And then we get this value here. This will be our like final prediction. And then remember, this is in log odds. So then we'll transform this back to prediction. So we go log odds to probability of final prediction. we get 0.89, right? So this is basically saying that we have a 90% chance this person will survive, based off of the initial prediction and based off of this one decision tree that we have. And we can kind of just check that by running the gradient boosting classifier on this example. So predict on X. And we get 1 because we can just round this. But anyways, so yeah, I know we can kind of change this. Let's say we want to go to like this branch here, right? So let's say we reduce the age to something less than 77. So we'll go to 50 here, set that, and then we run through. The initial prediction stays the same, initial log odds is the same. The predicted log odds is different because we're now in a different branch of the decision tree. And then the final prediction is going to be different. So then we find the log odds to probability, and now we have a 0.2%. And so this will be classified with 0, as shown here. So that's the general gist of how this works. I mean, it's pretty simple, initial value, and then just multiple decision trees. And yeah, that's basically it. That's basically the end of the workshop. Thanks for attending. And let me know if you have any questions. Otherwise, I'll end the recording here and you're all free to go. And yeah, remember to fill out the raffle, the feedback form to make sure that you enter in the raffle for, I think, Amazon gift card. And if you haven't signed up to be a member, that's the sign up link. But yeah, thanks for coming. I'll stop recording here.